and make it not just a kind of one-person contribution. Right, so we did lots of definitions last time, and unfortunately there are a few more to go through. The first kind of set of remarks I want to make is about different kinds of representation. And there's a departure from the kind of classical representation theory developed over complex numbers, because for bifurcation purposes, naturally the object that you're given is a set of differential equations on Rn, so there are some distinctions to make. So that's the first thing that we're going to do. Then we're going to try and sort of bring the differential equations back in after the algebra, and I want to get to the equivariant branching lemma, and then hopefully do an example and sort of bring it maybe back to liquid crystals even, and that'll be enough, I reckon. So I have some kind of sketchy notes. I put on the forum a link to other types notes which are hopefully at least legible. So I'm just going to remind you of where we kind of finished last time. We had a real representation is a homomorphism which I call rho tilde, and it's a map from our finite or compact Lie groups into the set of n by n invertible matrices with real entries, and in fact it's good enough to think about orthogonal matrices. And then we had a definition last time. We said sort of rho tilde is said to be an irreducible representation, or just irrec, if the only invariant subspaces of Rn are the kind of trivial ones, 0 and Rn. Okay, so there are no non-trivial proper invariant subspaces. I can't write Rn as a direct sum V plus V perpendicular, and I have a separate action on V and its complement. So I want to introduce a refinement of this idea. So rho tilde is going to be said to be absolutely irreducible. If whenever A is a commuting linear map on Rn, then A is actually forced to be some real multiple of the n by n identity matrix in the right coordinate. Okay. So this is a refinement of the idea of irreducibility in the sense that.
And with commuting linear map, you mean they commute with all members of the group?
Yes, yes. So I mean,
so it's equivariant.
Hang on. A rho tilde G is rho tilde G A floor G G. Okay, so it's pretty much the only thing you could.
So isn't that the same as saying it's an equivariant linear map?
Yes, but I'm not. I haven't got the word equivariant. I've only used the word equivariant for my differential equations. Okay, so there is a connection to be made, but pedagogically, I'm not yet making it.
No, sorry, I thought you had used that term.
No. Well, I have, but only for the differential equation.
So if you had a linear differential equation.
Yeah. I mean, I will. Okay.
Okay.
That's sort of over on the board underneath here. Okay. I now have to space out the writing to get there. Yeah. Okay. So lemma absolute irreducibility implies irreducibility. Okay. Which you might hope, and the sort of the simple proof is to prove the contrapositive of this, so that I suppose that I'm reducible. Okay, then if I'm reducible, I can write Rn as this direct sum decomposition. I have a separate action on each of these. Okay, so I can simply take an A, which is some multiple of the identity matrix on each part. They don't have to be the same multiple. Okay, so then clearly this is a commuting linear map. Okay, but there's no sort of single C necessarily for A. So I have a set of commuting linear maps that's larger than just multiples of the identity, so I am not absolutely irreducible. Okay? So that's not B implies not A is equivalent to A implies B. So then there's a version of Schur's lemma for irreducible real representations as we've been developing them. So this collection of commuting linear maps, one can ask, what does it look like? Okay. So in the right coordinates. So it's either real multiples of the identity matrix, or it's complex multiples of the identity matrix, or it's quaternionic multiples of the identity matrix. Okay? This is a result sort of in algebra. Okay, this is Frobenius theorem. Okay, and that implies that there are only these three choices, and the reason is that the set of commuting linear maps is a set with some structure, and it has the structure of an associative skew field, and Frobenius' theorem is that over the real numbers there are only three distinct associative skew fields, and these are they. So that's the motivation. It's a purely algebraic idea. So for our purposes, okay, they're going to be useful, and I'm going to write them in a sort of suggestive notation. Okay, this is going to be something that looks like C plus I omega times the identity, or if I wrote that in different coordinates, we would have a set of commuting linear maps in the right coordinates in Jordan forms. It will look like this. Okay, times the identity of size n over 2. Okay. So this is going to correspond, in a sense, to our generic case for steady state bifurcation, case 1. Case 2 is going to be our natural setting for, or the natural bifurcation problem in the second setting will be oscillatory bifurcation, and the third case doesn't appear to be useful in bifurcation contexts. So this is our kind of distinction. So then to sort of pick up David's point, why is this a useful classification? Okay, and the answer is that we naturally have a commuting linear map because our equivariance condition for the differential equations, okay, so we've always got differential equations x dot is f of x mu in Rn, and we observed before that it was natural to demand that f of gx comma mu was g times f of x mu. Okay, and when I write g now, I'm thinking of rho tilde of g. I've got one representation in mind. So if I differentiate this, then I have the Jacobian matrix evaluated at g of x comma mu multiplied by g. So this is just matrix multiplication, is df evaluated at x comma mu. Okay, G is linear. So if I set x equal to 0, then G 0 is 0, x is 0. So I have a natural commuting linear map, which is the linearization of my differential equations at the origin. Okay? So GF 0 mu is a commuting linear map. Okay, so then the sort of the natural idea is that it's going to look like, for the case of steady state bifurcation, it's going to, in the right coordinates, be a multiple of the identity, and then for off bifurcation, it's going to have eigenvalues that have multiplicity n over 2 and are crossing the imaginary axis at some non-zero value, plus or minus I omega. So steady state bifurcation is generic in case 1, oscillatory bifurcation in case 2. So I'm writing this slightly carefully because there's another sort of possibility for oscillatory bifurcation when I have not quite a single irreducible but not absolutely irreducible representation, but I have two copies of the same absolutely irreducible representation. So I'm not really going to discuss oscillatory bifurcation, so I'm not going to do that in any more detail, just to say it's there. Okay. So this is the kind of the typical context. There's one other remark that's probably worth making now. So if G acts absolutely irreducibly, then f of 0 mu is 0 for all mu. Okay, so being absolutely irreducible implies that I have an equilibrium point at the origin. Okay, so this is because I've got f at 0 mu from the equivariance condition, G is linear, is G times f of 0 mu. Okay, so f is an object that is fixed under all G. Okay, so if I think about multiples of f, those span a one-dimensional line, okay, in Rn, and that's an invariant subspace. Okay, that's a V, so that I can then break Rn up into V plus its perpendicular complement. Okay, and that contradicts my definition of my representation being absolutely irreducible.
In fact, here you just need irreducibility, and you contradicted just the effect of the irreducibility, not the absolute irreducibility.
I did, you're right. Okay, but this is definitely...
Yes, but I mean, if you look at it from a pure point of view, you can
Yes.
you can remove absolute here, and you can make the next statement that absolute irreducibility implies something about the linearization at 0.
Yes, which I sort of did.
Which comes from the
Already.
fact up there, yes. But
Yeah.
which is maybe worth noting. That the
Yes.
the linearization is a multiple of the identity.
Yeah,
Which is important for bifurcation, in fact.
sure. Okay, so I'll say this. And a one-dimensional subspace V if not 0. Okay, so I'll say that, and then if G acts absolutely irreducibly, then the linearization is a real multiple of the identity by above. Okay? So this is our kind of starting point for investigating a bifurcation problem in the generic context of G acting by one of its absolutely irreducible representations. Okay? So there are kind of other questions that I'm not going to address, such as how do I go about computing how many irreducible representations G has, and then which ones of those are absolutely irreducible. But at least if somebody gives you a representation, then you can check that it is irreducible or absolutely irreducible. Okay, so we've got enough terminology to know when we're in this generic context. So the equivariant branching lemma is then the kind of the tool to tell you what to expect if you had such a bifurcation. So I need a couple of definitions and then what do I need? I suppose I need 3 definitions and a little kind of one-line lemma before I actually give you this thing. Okay, but this is all kind of one section because it's one connected thread of ideas. So I have to define a couple of kind of complementary ideas. So far we've talked about how much symmetry the whole problem has. Okay, in the sense that G is my collection of symmetry operations acting on the whole phase space. Now we want to be a little bit more specific and talk about if I have one particular point in my phase space or one solution trajectory, how much symmetry does that particular point have? Okay, and different points in my phase space naturally come with different subgroups of our symmetry group. So given a point X in the phase space, I'm going to define an isotropy subgroup sigma X, so that's a subgroup of G. So this is defined to be the set of group elements that fix that point. Okay? So it's a natural idea of the kind of symmetry that's available at a point. The kind of complementary definition is to say, if I have a subgroup, what are the points that are fixed? So given a not necessarily isotropy, just any subgroup, sigma in G, we can define the fixed point subspace. So this is fix of sigma, and this is just a collection of points in my phase space that satisfy Gx is X for all G in sigma. So, yeah, should be a little sigma in big sigma.
Ask a question.
Yeah.
If you go back to here, what's the significance of X being 0 in this last thing? So you got.
So it was only, this thing was only a commuting linear map when X was 0, because actually this was evaluating the Jacobian of Gx, and this was evaluating it of X.
Okay, if you go raise it again, I'm sorry. But all right. So but the second line is true for any X, correct? The second line, FGX mu equals GFX mu.
Yes, so that's our equivariance condition.
So does that mean that everything should be 0?
No, so I just differentiated that and got Jacobian of Gx times G is G times Jacobian of X. Okay.
But if F equals GF, our second line here, and if that's true for that says if you took any X, you'd have F of X mu equals G of F of X mu. So if F of X mu is non-zero, it would be an invariant.
I'm not following you.
Oh, it's only for 0.
Yeah, I've specified, I've put X equal to 0 in this.
So x equals 0 is the only one where you see the commutativity.
So because G is linear, I know that G0 is 0. So here I've got the same thing on each side. Okay, I have exactly the same object. Okay, so this says there's a particular direction.
Okay, I see. Yeah, G of 0 is 0. Okay, thank you. Yeah.
Right. Okay. No problem. Is everybody happy? You happy, mate? You're happy?
Maybe one remark. I mean, of course, this condition which you wrote down for 0, you can translate into other points if you look at the symmetry of these points. I mean, so this is something which applies to the point 0, and sometimes for linear maps you try to do things at other points. But then you look at the symmetry of this point, and if you have points with full symmetry, this would, similar things would be true at other points as well.
Mm. I've ruled out having any other point with full symmetry.
Yeah. But of course, if you, for example, go down to the subgroups of your group, then you can look at the normalizer and have action of the normalizer on subsets. I know you will come there, but I just wanted to point out that this condition, which seems very special, is very natural if you look at more general types of problems.
Okay.
Yes.
Actually, these sort of equations are known in physics as Landau-Khalatnikov equations for relaxation.
Okay.
Which is on the left-hand side.
Which one?
The one at the top.
Okay.
X prime represents, say, the time derivative of the order parameter, while fx mu represents the Landau free energy derivation over the order parameter times gamma times minus.
Okay.
So that's roughly a non-linear type of equation that describes relaxation of the order parameter. And then this condition is natural to me.
Yes.
So how did you call it? Landau?
Landau-Khalatnikov.
Khalatnikov.
Yeah.
Okay.
Very good.
This is relaxation. Relaxation of the order parameter.
Yeah.
Just like the gradient flow associated.
Exactly.
Yes.
Yeah.
So you get
So it's the
vector.
it's the statement that if the function is invariant, then the gradient flow is equivariant.
Yeah.
Basically the same.
Yeah, exactly.
Well,
Well, it's good to learn a few new names.
yeah.
I mean, this is the main purpose of this. Yeah.
Yes, exactly.
It's another entry in the dictionary
Yeah.
for translating.
We must try to work this into some papers. Yeah.
Yes.
You could write sort of 2 versions of each paragraph.
Depends where you want to publish it.
Remember, this discussion is being recorded. So any further pseudo-scientific
He
discussion.
did not suggest to publish it twice. I mean,
No, of course. I would never do such a thing.
I wondered if there was something like that coming.
We're being filmed. Podcast.
I don't know. I think maybe you're behind being filmed, but you're just all being recorded. So.
No, look at that one.
Oh, is that one? Okay.
Oh,
It's
off
off
right
right
now.
the camera.
Someone's watching you now.
I think that one is watching me.
No, the one with the red light is on.
The one with the red light is on. Okay,
That's
so
the
it can
back.
see all the backs of your head.
And now
Need to get police.
The last 30 seconds can be edited out without scientific integrity. Okay. So we have these 2 kind of ideas that are almost dual to each other, but not quite. And this is going to be useful terminology in a moment. So there's one very important property of fixed point subspaces that we're going to rely on. So I want to discuss that. And the idea of these fixed point subspaces is that once you kind of start in a hyperplane, okay, on which you have some symmetry, you have a collection of points that are all left alone by some subgroup of the original group, then actually your dynamics, if you have equivariant ODEs, you will remain in that hyperplane, okay? So pick some subgroup, sigma, then fix sigma is flow invariant, as it were, for my vector field F. And the proof of this is a kind of, so it's very simple. The idea is just that the tangent vector remains in that plane. So if I'm given an x as a kind of starting, let's have an x naught. Okay. And, sorry, it should be a sigma of G in my subgroup. Then I have G acting on x dot, okay, is GS, so it's just my x dot is f of x. I've acted by G on both sides. And I'm then going to use the equivariance property, which is true for all G and G, so certainly true for these G's, okay, so that's equivariance. And then actually for the G's that are in sigma, okay, they fix these elements. So that's just going to be f of x, okay? And then this f of x from the differential equation, this is just x dot. So I've just said that x dot, okay, the tangent vector is fixed, okay? So that means if I integrate along curves, then this is x dot dt primed. So if I just carry out this integration, then I've got that g x of t minus gx0 is x of t minus x0. Okay? So if I started off with some point where x0 is equal to gx0, then as I integrate along this curve, gx of t is equal to x of t. Okay?
You can never launch yourself into a space of higher symmetry, basically.
Absolutely.
You can only go into lower symmetry.
No.
I can't. I can only kind of asymptotically get to lower symmetry. Stay in.
But you cannot go into lower symmetry. You always stay in the space in the same symmetry. And asymptotically you can approach points with higher symmetry, but not with lower symmetry.
So I can imagine how there was
Thinking of a
dynamics.
I mean, if you have a solution x of t, and then you can have
point
the
that's
limit
not
x of
symmetry.
t is x.
But I'm only getting there asymptotically.
T goes to infinity.
Yeah.
And,
So for any fixed bounded time interval, I've got the same isotropy that I started with.
when you say higher symmetry means it's in the fixed space of a supergroup of your.
So it's in a lower dimensional. It's heading towards a point that's in a lower dimensional hyperplane. Okay.
You did not say that the fixed point spaces come in linear subspaces of the.
I did not. I can scale x by a factor here, so this is a linear subspace.
Yeah, no, but I mean it's worth pointing out. But of course, the same statement is true if you, for example, work on manifolds, and then you have precisely the same statement. That the fixed point space remains invariant, and you only approach points with higher symmetry asymptotically, and but you can never approach points with lower symmetry. They are around you. I mean, you are in a space with higher symmetry, and next to you there are many points, like in this picture, with lower symmetry, but you cannot get into this space.
This is for a fixed value of parameter mu, of course. But then, I mean, the whole game is when you change mu, what happens? But, at the moment, it's a fixed parameter value.
But even if you change mu, I mean, if you have an initial value with a certain symmetry, you keep this symmetry whatever you do.
Yeah. My collection of ODEs that I is G equivariant for all mu.
Yeah.
So this is a
Yeah,
mu
it's true,
independent
it's true, yeah.
idea. Yeah. The dynamics might change, what actually happens, but the stratification of my Rn into these hyperplanes.
Yeah.
So think about a collection of linear subspaces and their intersections. Okay, so I've got an Rn, which is this kind of amorphous object, and then I kind of slice through it. Okay, and whenever I slice through it, the intersection of these two slices is a hyperplane of lower dimension, then it has more symmetry. Okay?
Your two slices are different fixed spaces.
That's right. Yes.
Right.
So I now want some kind of some better drawing skills. What I want. Very good. Okay. So this is, you know.
You've been practicing.
I pick two subgroups, okay? They have some fixed point subspaces, and then everything in the intersection, fix sigma 1 intersect fix sigma 2, picks up all the isotropy around. Okay? And then the origin, okay, has full symmetry, and if I have this absolutely reducible representation, then it's the only point that has full symmetry. Okay? So I've really sort of said everything about how to decompose Rn. So being absolutely reducible is quite a strong constraint, but it's the natural one for thinking about steady state bifurcation.
Of course, in physics rather than in maths, you have some noise, and then you might actually go somewhere different, but that's different.
What happens if you add noise? It's always the question. Okay.
No, but I mean, I don't,
Yeah.
not being too frivolous, but I mean, of course, in mathematics we look at solutions and so on, whereas physics you're very much oriented to stable, robust solutions.
Yes. Yes. So.
That's an issue to say, but anyway.
Yeah, that's right, and there are plenty of interesting effects where you see measurements or sort of simulation results that are hovering close to some symmetry subspace, and then maybe after a while they sort of make some transition away and they're close to some other symmetry subspace. Okay, so noise is one mechanism for driving you towards that. It's also possible to have sort of just slightly more complicated dynamics than you're used to, in the sense that you can have dynamics on the axes. If the axes are invariant, if they're fixed by some reflection symmetry in that axis, but I know that trajectories are kind of coming in from large amplitudes, then I can have an unstable focus, and my trajectory can get incredibly close to these axes, okay? And it can just kind of make larger and larger excursions, taking longer and longer amounts of time, because it can't actually sort of get into the invariant set that is the two axes. Okay, so I can have lots of sort of non-ergodic dynamics through the existence of these invariant subspaces. Okay, I can never actually land on an axis; I just get very close to it. So anyway, I promised you an equivariant branching lemma. So the simplest case of all this, okay, is a subgroup, or an isotropy subgroup, so that's sigma an isotropy subgroup such that the dimension of the fixed point space of sigma is 1. Okay? And these are useful enough to get a name. So if I have a one-dimensional fixed point subspace, that's just a line in my phase space, so these are called axial isotropy subgroups. Okay. So now we have enough terminology to state what happens, or at least some indication of what happens at a steady state bifurcation. So I'm going to be in the standard setup. Okay, so G is going to be a compact Lie group. It's going to act absolutely irreducibly. Okay, so G compact Lie absolutely irreducible, and I've got my traditional ODEs. X dot is f of x mu, are G equivariant. Okay, so then we've seen already that it follows that the origin is an equilibrium point for all mu. Okay, f0 mu is 0 for all mu. Okay, that's absolute irreducibility. Okay, and we've also seen, really by definition, absolute irreducibly, that the Jacobian matrix is going to be some real multiple of the identity. So C of mu is real values. And then to actually have a bifurcation, so I've got a collection of eigenvalues in my linearization now that are sitting on the real axis, and I'm thinking about watching them pass across the imaginary axis, okay? And they should do this in a kind of non-degenerate bifurcation sense. So I want to get some zero eigenvalues, so without loss of generality, I'm going to assume that C of 0 is 0, just so that my bifurcation happens when mu is 0. Okay, and that they cross the axis with non-zero speed. Okay, so this is a transversality condition to say that my eigenvalues really go up to 0 and then all the way through as I vary mu. Okay, it's quite, unlikely that they would get all the way up to 0 and then come back on the same side. I just want to rule that out as a possibility. Okay. So then, given all this setup, there exists a branch of solutions, equilibrium points, okay, satisfying f of x of mu when mu is 0. Sorry, this is logistically horrible. Yeah. Okay, so exists a branch of solutions f of x mu, comma mu is 0 for each axial isotropy subgroup sigma in G, and it's a branch of solutions that has the isotropy sigma that you first thought of. So sigma x of mu is sigma for mu that are not zero. So my idea is that I've got an equilibrium point at the origin. So if I draw a bifurcation diagram, okay, so I have mu this way, I have some kind of size of my points, okay, some indicator of size of these equilibria, and I'm thinking that I have a branch that is stable. So suppose that my eigenvalues are on the left of the imaginary axis when mu is negative. So I have a bifurcation point. I always have an equilibrium at the origin. It's going unstable as mu increases through 0. And then there's some collection of curves that comes out. Okay, and these curves, I have one curve which is some branch x as a function of mu. Okay, one of these for each axial isotropy subgroup. So if I start with a group G and an absolutely irreducible representation, I can then try and identify axial isotropy subgroups. So isotropy subgroups that have one-dimensional fixed-point subspaces. And the equivariant branching lemma guarantees the existence of a new curve of equilibrium solutions sort of coming out of my bifurcation point at the origin.
This is stronger than so this guarantees existence of these branches. It's not suggesting what you might expect to see. It's saying these are here, right?
Yeah.
Under these assumptions.
And you know, various kind of non-degeneracy conditions. So, but you know, typically.
What happens for negative mu?
So I don't know the direction this comes off in. Okay, I just said so that it might be that I have a, you know, there's quite possibly more than one of these, and the branching direction is going to be given by my solution to this. Okay. So when we do some worked examples, we'll actually write down some. So we have lots of information about f because it's an equivariant vector. Okay, so we can write down the most general form of f for a given representation, and then we'll have some coefficients in front of these various terms. We can take a kind of normal form approach and write down the first few polynomial terms. Okay, and hoping that we've gone far enough so that we can identify generic branching behavior, we'll then have conditions on those coefficients that tell us which direction the branches actually go in. Okay? But at the moment I don't know, I'm just drawing something schematic. Okay?
One-dimensionality of the isotropic, the axiality of these isotropic
Yes.
groups must be pretty crucial here, I gather.
Yeah. So the one-dimensionality is the key to the story. So usually, for bifurcation without symmetry, problems in one dimension are kind of straightforward, and we have saddle node, pitchfork, transcritical, this kind of thing. And then when you're faced with a sort of a higher dimensional set of differential equations, you have some argument that's called a center manifold reduction or a Lyapunov-Schmidt calculation that says that I have a load of other eigenvalues, okay, that are bounded away from the imaginary axis. I just have one interesting eigenvalue at 0. So then I can eliminate all those other variables and write them in terms of a center manifold variable that corresponds to the eigendirection of the eigenvalue that is crossing the imaginary axis. Okay, so there's a kind of reduction procedure from my Rn down to a one-dimensional or a two-dimensional problem. Okay, here, because of all the linear structure that I have from the group action, I've got this collection of one-dimensional spaces and their flow invariants from symmetry. So actually all I'm doing is saying that within my Rn I have this collection of lines that are flow invariant, so I can restrict my dynamics just to that line, and then I have a one-dimensional bifurcation problem. And these conditions assure me that I have a generic one-dimensional bifurcation problem, but I can do one-dimensional bifurcation problems. So the symmetry provides the reduction procedure that otherwise would be center manifold or Lyapunov-Schmidt or something. So it's really saying I can consider each of these lines in turn, okay, because each one is flow invariant and it's just a line. And that's essentially the proof.
Maybe two remarks. One is, of course, there is no guarantee that such spaces exist.
No?
No.
Did I guarantee that?
No, I just wanted to point. No, you did not guarantee that. I just wanted to point it out.
Yes.
Because symmetry implies, but there might be symmetric situations where you don't find one-dimensional spaces.
Okay, yes.
And then, of course, you might have to discuss higher dimensional bifurcation equations.
Yep, as you have done, I think.
As I have done, yes.
Yes.
No, but I mean, I think it's important information that it's not automatic that you get one-dimensional spaces.
Yeah.
And the second is, of course, there is also a center manifold reduction in symmetric context, because you might have a high-dimensional problem which you decompose into a low-dimensional problem and another high-dimensional problem, and you restrict. And generically, the low-dimensional problem is absolutely irreducible representation of the group.
Yeah.
So this is a very natural assumption, which from center manifold theory, one can see this is a very natural assumption to assume absolute irreducibility.
Thank you very much. Yes, that was your second remark was something that I decided not to talk about, just to kind of launch straight into the...
But since your answer have any fault, I thought I should add.
Yes, that's absolutely.
But if you didn't know anything about equivariant bifurcation theory and you had one of these problems and you attacked it with center manifold theory, you would actually get this line as your center manifold.
Yeah, I suppose you would. You would say, here is my approximation to the center manifold. I have a linear term, and then I have a load of other terms. They're all zero. I suppose I can guarantee that there are no exponentially flat contributions, which for center manifolds in general there might be.
Secretly, the theory is telling you that actually this line is
a line.
Is going to work.
Yes, you can relax. It's a line.
Just another third remark, just to relate into what Andrew is saying. I mean, your picture there, you've done mod x. You've got a mod x-axis.
Yes.
I mean, if you had an actual x-axis, then you have a curve going right through the origin. I mean, it might go from right, or it might be tangent to the x-axis, but there is always a curve that goes right through. So, in a sort of partial answer to what Andrew said, you either have a solution both for positive and negative mu, or if that fails, you have none on one side and 2 on the other.
Yes. Yes, good point. Because, so one can see that just because there is a one-dimensional bifurcation problem to be done, in the sense that, so you assume that you have a one-dimensional, an isotropy subgroup with a one-dimensional fixed point space, and then within that fixed point space, x dot is f of x mu, I can just look at the restriction of my dynamics to fixed sigma, and I have some one-dimensional equation with some coefficients, okay, and I'm assuming that everything is sort of smooth and so on. Okay, so this is really a one-dimensional differential equation, okay? So C of mu, so the linear term is exactly the same linear term as I had before, and then I can sort of calculate some Taylor coefficients, which might depend on my parameter mu, okay, and then this gives you the branching behavior, okay? So then I'm interested in sort of what G1, G2 evaluate to for small mu, okay? So in this sense, now apply standard one-dimensional bifurcation results, and your favorite IFT, okay, inverse function theorem or implicit function theorem, and then our kind of one-dimensional conclusion. So we always have an equilibrium point y equals 0, okay. So I'm not quite in the generic case, but we would expect within this subspace to see something transcritical if G1 of 0 is non-zero, or something that's pitchfork if G1 of 0 is 0, but G2 of 0 is not 0. Okay. And then maybe, symmetry might help us here. So there is more to say that will be said, in fact, on the next page. Okay, good. So we know a little bit more. So yeah, I never wrote proof, but this is kind of. This is as much as I'm going to do for proof, okay? Because it's this and the geometric picture we built up. Okay. So we also have symmetry constraints within this, within any fixed point space of an isotropy subgroup, but certainly here. So I let sigma and G be an isotropy subgroup. Then K, which is the normalizer in G of sigma, quotiented by sigma itself, exactly the symmetries that act non-trivially on the fixed signal. So the normalizer is the largest subgroup of G that maps fixed sigma to itself. So this is a way of, I know the normalizer, okay, so sigma acts trivially on fixed sigma, okay, that's what fixed sigma means. So I can get rid of those and I can sort of ask questions about whether the normalizer is larger than sigma, and if it is, then I have some additional constraints, which gives me additional information about the form of this y dot equation, for example.
I'm sorry, can you tell me where
Yeah.
the y dot equation comes from? And
Sure.
we had this branch of equivariant steady states.
Yes.
And now,
Now where's y? So y is it's a coordinate, okay, along my one-dimensional line, which is my fixed point subspace.
I thought those were all steady states. Why are you moving along that? That's why I don't quite.
Well, so that's what y measures. So I'm now trying to look at the dynamics within that line.
But the steady, I thought they were, if you started on a point on that line, it would be, x dot would be 0.
So I have an invariant. So I have a line that is invariant under my symmetry.
Yeah.
It's not invariant under the vector field.
But f of it will be 0 and x dot equals out.
So there are equilibrium points,
Yeah.
but this equation will have equilibrium points that correspond to those that I said were branches, were functions of mu. Okay, so I can find those by putting that equal to 0. But this is telling me about the behavior away from those equilibrium.
Okay.
Okay, so I can use this to check stability, for example, at least within that line. Okay, so the nice way to say the theorem that I've just stated is that the dynamics in fixed sigma is equivariant under this group K that I've just defined. So it's actually n sigma equivariant, but sigma acts trivially. Okay. So in the case that I'm axial, okay, so if dim fixed sigma is 1, then there are only two choices. Okay, so if I have a line, and I think about what this normalizer could look like, and it's a collection of symmetry elements that map the line into itself, there are only two possibilities. Either it fixes every point on the line, okay, and everything acts as the identity, or there are some elements that take x to minus x along the line, act as minus the identity. Okay. So these two possibilities are that K looks like just the identity element, okay, or K looks like the identity element and minus the identity. Okay, so in other words, it's a Z2 group. Okay, so in this case, there's no more information, and we might anticipate having a transcritical Okay, just because if you don't tell me anything else, then I'm expecting that this G1 coefficient is not 0. Okay, that's what one might think is the generic case. In this case, I have something that kills even order terms in my y dot equation. Yeah?
We're just mumbling, sorry.
You want an example?
Good video.
You guessed it. Yeah.
Luckily. Okay. Yeah, we started close to on time. I think, actually.
Well, we've been asking a lot of questions.
Okay, so right. So let's do the example, and then we can. So there is 24 to 7. So the natural example to do, I thought, was the D3 example. Because it has the kind of liquid crystal interpretation. I'm not going to, as it were, do the interpretation. I'm just going to do the bifurcation problem. Okay, and you can take your the isotropic to nematic transition is going to be the sort of interpretation of all this. So I'm going to think about D3 in the kind of natural action that it has on the plane R2, and in a very concrete way I'm going to sort of give you a complete set of the elements. Okay, so D3 has 6 elements. There's an identity operation, rotations by 2 pi by 3 and 4 pi by 3, and then some mirror symmetries, and I'm going to call a reflection in the x-axis mx, and then a diagonal reflection md. M is the mirror, and then a d prime. Okay, so there are 6 elements. So order D3 is 6. See picture. And then I'm going to describe the action by using the identification of R2 with the complex numbers. Okay, so I'm still going to have an absolutely irreducible problem. It's just for labeling convenience that I'm going to, instead of doing everything with points x and y in the plane, I'm going to use one complex variable, just because it makes writing everything down so much faster. So these are, the action is specified by the action of the generators. So I have rho acting on z as a rotation is just multiplication by that complex number, and then the mirror symmetry takes a point z to z bar. Okay. So then if I want to look at, to apply the machinery, first of all I can check that this is indeed an absolutely irreducible representation. And then I know that the branching lemma guarantees the existence of branches when I find axial isotropy subgroups. Okay, so there turns out to be a subgroup consisting of the identity and the reflection symmetry. Okay, so fix of sigma is the set of points that are real. Okay. So this is clearly one-dimensional, and it is the only such up to conjugacy. Okay, so there are also conjugate axial isotropy subgroups. That fix rho times fix sigma, and rho squared times fix sigma. Okay, so if I fix the axis, I also fix these lines that I've indicated by MD and MD prime. Okay, but they're all conjugate to each other. Okay, so they have the same dynamics. So there's one group orbit of these isotropy subgroups that has these 3 lines. So then the equivariant branching lemma implies bifurcation produces new branches that have symmetry sigma. Okay? And then we can also compute the normalizer. Okay? So n sigma over sigma, in this case, is just the identity element. Okay? So we're not sure if these are transcritical or pitchfork at this point, in fact. But we can do some calculations, so we can look at the amplitude equation, okay, or the bifurcation equation, and in fact it's not too hard to kind of knock out something better than what I'm going to do to tell you really everything, all the structure of the equivariant vector field that I'm going to write in this form. So instead of x and y, I've got independent coordinates z and z bar. Okay, but you can take real and imaginary parts of everything, and I'll do this in a moment. So what are my constraints on f, okay, to make it D3 equivariant? It's enough just to check equivariance on the generators. So looking at rotational equivariance, okay, so this is take a z and rotate it, and then apply f. That's the same as taking a z, applying f, and then rotating, okay? So I want this, and I also want to take a z, apply complex conjugation, and then apply f, and that's the same as taking a z, applying f, and then applying complex conjugation, okay? So these are constraints on the form of f. So if I look at terms that satisfy this, okay, so it's kind of linear, so I can work one polynomial term at a time. So if I try something that looks like z to the p, z bar to the q, integer p and q, okay, then my constraint here tells me that in terms of the multiples of e to the 2 pi by 3 that I pick up, okay, I have, yeah, let's write it this way around. So I have p of them, I have a z to the p, I have p multiples from here, minus q of them, okay, for my second term, that needs to be 1, because I have one multiple of e to the 2 pi over 3 on the right-hand side, modulo 3. And then from the second equation, I have a coefficient alpha in there. This tells me that alpha, as it were, yeah, so it's right. Alpha z bar to the p, z to the q should be alpha z to the p, z bar to the q complex conjugate. So this tells me nothing except that alpha bar needs to be equal to alpha. Okay? So alpha needs to be real, and p is 1 plus q mod 3. So I can have p equals 1, q equals 0, p equals 0, q equals 2, and then a kind of general term, p is 1 plus q. Okay. So this gives me a term that looks like z, this gives me a term that looks like z bar squared, and this gives me a term that looks like z mod z to the 2p to q. Okay? So there's a sort of complete way of writing this in terms of equivariant and invariant polynomials. This is in fact everything for this case. So in terms of a kind of Taylor series, looking at my lowest order terms, I've got real coefficients everywhere. I have a linear term in z, so I've given the coefficient just mu. I've got a real coefficient times a term in z bar squared, and then something that looks like the z mod z squared, and higher order things. Okay, so this is the structure of my D3 symmetric vector field. Okay, So then if I want to write this down in kind of real and imaginary coordinates, it just looks slightly less obvious. Okay. So I have a diagonal thing here. It must be a real multiple of the identity by what we've done before. And then here I have something that you might not immediately have guessed. Okay. And then I have an x squared plus y squared in the radial direction. Okay. So these are equivalent, but this is obviously nicer to work with. But then we can do useful things with the sort of real representation, sort of the real version of this, because if b is non-zero, then if I want to look at stability, okay, so clearly here,
which is
so I've just got, yeah, so this is a x minus I.
yeah, sorry.
Okay. So if b is non-zero, then I'd expect these terms to dominate these ones near the bifurcation point. So if I look at a branch that I know should exist on symmetry grounds, so the branch x0 satisfies some bifurcation equation. Yeah, so I have a mu x plus bx squared plus cx cubed and so on. And I can set y to be 0, and that's clearly fine for my second component here. Okay? So if I think about being at small x, then x is approximately, its location is given by approximately minus mu over b. Okay? So if I then think about stability, okay, my Jacobian matrix is going to roughly look like mu plus 2xb minus 2by mu minus 2x and then a minus 2by. Okay, so I'm doing this just to sort of pull out something that is slightly unusual, okay, in the sense that j evaluated now at minus mu over b0 is approximately for small x, so there's a minus mu over b I'm putting in here, so there's a minus mu in that corner, the zeros here, and then that x is minus mu over b, so that's mu plus 2 mu, so that's 3 mu, okay? So for all non-zero mu, I have eigenvalues of opposite sign, okay? So this means that although my bifurcation equation tells me that this is transcritical, okay, so I would expect, I'm sketching b positive here, so this is x function of mu, so I'd expect this branch to be stable, and it is indeed stable within this fixed point subspace. It's unstable in the transverse direction, okay? So in fact, for this particular problem, it's not the one-dimensional transcritical case, okay? So these are the signs of my eigenvalues. So this is the local branching behavior and stability for the bifurcation problem with D3 symmetry. Okay? And there are sort of better ways of putting this in a general context, but it's not a very difficult calculation to see that this must be the case for this specific problem. So then the kind of, so I'm going to stick with B positive now, just to sort of sketch what's going on in the phase plane. So we know that we have these invariant lines, okay? So I have fixed points out here, so if mu is negative, okay, so these are the pictures in the paper that David has been talking about. There's a point at the origin, which is my point of full isotropy, and I'm I have branch, I have kind of stability sort of designations like this. Yeah. So there's lots of off-axis stuff that can be made to look convincing if I sketch things slightly more slowly. Maybe I'll try on this side. So this is mu positive, so I have 3 points here that are related by symmetry, they're on one group orbit. Okay, and in the liquid crystal interpretation, I have an isotropic, a fully symmetric state in the middle, and I'm picking a coordinate frame to describe the local alignment, but all permutation possibilities of those axes are allowed. So there's permutation symmetry between my labeling of x, y, z, and that permutation group is exactly the same group as D3. So I have some representation in terms of two order parameters, S and P, that says I have 3 possible nematic phases that are related to each other by rotation of my coordinate axes, and it's just a labeling problem, but they are physically indistinguishable. Okay, so I have 3 bulk states that are these nematic branches, and then as the temperature drops, as it were, I go to a state over here where I have these for the same 3 curves. And I've got some equilibrium points over here now. So I'm drawing the unstable manifolds of these 6 points. So continuity of arrows holds. So this is the sort of phase plane sketch behind the bifurcation diagram. The bifurcation has to look like this because it's constrained by symmetry. So we could go on. This is a reasonable place to stop, I think.
There should be. So this is your, I'm thinking liquid crystal wise.
Yeah.
So you've gone into the low temperature regime. The isotropic phase has become unstable. So you've got all the arrows going away from the origin.
Yes.
Now there shouldn't there be stable uniaxial
You want some stable thing to jump to.
yeah, because that's like the negatively ordered, the ones that are saddle nodes or whatever.
Yeah.
Those are like the negatively ordered uniaxial.
Yeah.
They're
Yes.
equilibria, but they're unstable.
Exactly.
But or there should be stable.
Uniaxial problem.
Yeah.
Yeah.
Yeah. So this is all a local analysis near that bifurcation point. The natural thing to do, I drop the cubic term. Okay. I just thought about the linear term and the quadratic term. But if we put the cubic term back in with a kind of decent negative coefficient, okay, then we should be able to take our modification diagram and extend it to make something like that.
Okay.
Which would then be physically much more satisfying.
I see, but this is just the local picture in the
Yes.
vicinity of the bifurcation point.
And this was all that I could guarantee, because a bifurcation result is a local bifurcation result is only a local. So it's local in X and therefore local in V. But out here, you've got something that is what you'd actually dynamically head to when you went through that instability.
And this is all now, and this is all rock solid, guaranteed, because your fixed space is one-dimensional. I mean, this isn't just a generic expected thing. This is
This is what it has to look like, and the subspace structure is there when I put in higher order terms.
The one generic assumption is that as mu, as the parameter value mu goes through the origin, then the eigenvalues of the linearization also.
Yeah.
Yeah, you want to say
Right,
proximity.
yeah.
The P is not zero.
Yeah.
There are two generic.
Sure.
Yes, so I could take it could happen that B was 0 as well, and then the picture would look different.
Yeah.
But that's,
Then
I
you,
mean, I think
then
Chuck
you would
was,
move your parabola into the point here.
Yeah.
Basically.
I think Chuck may feel that, you know, I mean, I've talked about generic stuff, it's a bit kind of hand wavy, you know, but I mean, it's precise in the sense that the generic assumption is that that is non-zero. So that's completely pinned down.
Yeah. One should always be able to write down a short list of conditions that define a closed zero measure subset of your parameter space.
Thank you very much, Sean.
Not a-